Alright, so in this lesson we're going to start looking at Newton's first law and equilibrium problems. And these are types of problems where an object is in a constant state of motion. Newton's first law says an object will stay in constant state of motion unless acted on by a net external force. This is what's called the law of inertia, Newton's first law. Basically what this is saying is if the sum of forces acting on an object is zero, the change in the motion of object or acceleration of that object is also zero. Now there are three key points to kind of point out about these types of situations. First one of these is that there are two possible scenarios where this is true. One of them is the object is at rest. The other one is the object is moving at a constant velocity, meaning same speed, same direction. Second point is that external forces can still act on the object as long as they add up in a way to cancel each other out. The third point is that vector addition is probably one of our best techniques for these types of situations, and what's true of all the vectors, if they're going to out, all have to add to be zero. Sample problem here, and here I have a stoplight with kilograms and its cable, and I want to figure out what is the tension in the cable. So my first step in any one of these problems, if we're dealing with forces, is to draw a free body diagram. So there's the stoplight, we have two forces, one is weight, the force due to gravity pulling down, and the other one is tension in the cable pulling up. So those are really the two forces that are acting on the stoplight. The way to calculate weight would be to take the mass, 50 kilograms, and multiply by the acceleration of gravity, 9.8. My second step is to apply Newton's first law. What Newton's first law is saying is that if this thing is at rest, which last time I saw a stoplight hanging from a cable, it's rest, that means the sum of all the forces acting on that object is zero. So what this would mean is that if I take the tension and add the weight, I should get, you might say, why is this negative? But where this negative sign comes in is the tension pulls up and weight pulls the opposite direction down. If I plug in what I know is true about weight, that weight is equal to mg, I get tension minus mg is equal to 0. So my third step here is to do some algebra addition. And what to do here is to add mg to both sides. And so I get the tension in the cable is equal to mg. Fifth step, plug in some math and calculate. 50 kilograms, 9.8 meters per second squared, so the test is 400 newtons. So if you look at the four steps, or the steps that I went through here, these are actually very similar to the steps that I went through when we did kinematics problems. Identify knowns and unknowns, write out my equation, find my relationships, solve for the unknown, then plug numbers in and calculate. As kind of a sample problem that is similar to this one is, what would happen if I take my stoplight with one cable and instead make it a stoplight supported by two vertical cables? What is the tension in either of the two cables? Now, we can probably ask a few questions. First question would be, would we expect the tension to be less than, equal to, or greater than the tension in the single cable problem? Probably if we have two cables, probably would expect the tension in each of those cables to be less than. And we can actually see that's true. Draw a free body diagram. There we go. I don't know why my second tension is not showing up, but I actually have two tensions. My second one will show up, both point up. I'm going to call them T1 and T2, and my weight pulls down. Apply Newton's first law, sum of forces equals 0, T1 plus minus W equals 0. There we go. There's nothing in this problem to suggest that T1 and T2 are not the same. In fact, it would prove that they are the same. We're going to make that assumption. So 2t minus w equals 0, or 2t minus mg equals 0. Now in this type of scenario, unless I had something to really tell me that one tension was bigger than the other, maybe one cable is on the center of the stoplight and one is on the outside of the stoplight, here look, they're both spaced in a way that they're going to equally share that weight. So do some algebra, solve for the unknown, add mg, divide by 2, and plug in some math, and what I get is tension is 245 newtons in either one of the two cables, half as big as what it was before. So as a corollary to this problem, let's take our two cables, and instead of making them two vertical cables, let's take those two cables and make them not vertical. And I've picked one to be at a 35-degree angle with the horizontal, and one to be at a 43-degree angle of the horizontal. So there are three questions to ask ourselves. First question is, are the tensions in the two cables the same? Second one is, if they're not the same, which which one of those is larger and why do you think it's larger? Third one, do the add up to equal the weight of the stoplight, meaning if I take the magnitude of the tension in the left-hand wire and add it to the magnitude in the right wire, do I get the weight of the stoplight? Do I get 490 newtons? So this is the end of this lesson. What we're going to do in the second version of equilibrium problems is start and answer these three questions about this scenario.